Okay, today we're going to talk about chapter 10, periodicity. Okay, part 2, chemical reactions and ceramics theory. Okay, hold on. Okay, so for today, let us clarify what we are going to learn. We are going to study the chemical reactions of any elements, of all the periodic elements, with oxygen, with chlorine, and with water. Okay. Then, after we study the reactions of elements with oxygen, chlorine, and water, then we're going to study about the chemical reactions of oxides with water, the acid-base reactions that oxides and hydroxides can do, and the reactions with chlorides. And that is what we're going to study about. Okay. So, at the end of the day, and then last one, we're going to talk a little bit about a subtopic called ceramics. Okay, so we're going to focus a little bit about ceramics. Okay. So now, let us start with the chemical reactions. It is very clear. This type of chapter, unfortunately, a lot of them you have to memorize. But the memorizing is not that difficult because they come and go roughly a bit similar. But there are few minor details that you have to observe. Okay? Let's talk about reactions of period 3 elements. We're going to observe it react with oxygen, chlorine, water. Then we're going to look at period 3 oxides, its chemical reactivity, and period 3 chlorides. Okay. Now let's start with elements with oxygen. When I say it is relatively straightforward, when it reacts with oxygen, it forms sodium oxide, magnesium oxide, aluminium oxide, okay, silicon dioxide, phosphorus tetraphosphorus decaoxide, P4O10. Okay. Now, unfortunately, you have to remember the color of the flame that it burns with. For sodium, it will be yellow flame. Magnesium, white flame. Aluminium, white flame. Phosphorus, white flame. Most of them, or close to all of them, will be white solid. I think this is relatively straightforward. This part a bit unfortunate. Now, please remember, when sodium burn, yellow flame, the rest all white flame. Okay. Now, you may say, sir, I have a hard time memorizing. But I just want to illustrate to you, if you think about it, don't worry of trying to memorize or balancing the equation. Just memorize what the product will be. And the product is relatively straightforward because O2 minus Na plus, O2 minus Mg2 plus, O2 minus Al3 plus, SiO2, now this one a bit of memorization, P4O10. Okay, now for this sulfur, so we have talked about, we're going to talk about 5 elements, we're going to talk about the 6th element. Sulfur can react with oxygen, okay, to form sulfur dioxide. You have learned that in chapter 8, the contact process. Now, then sulfur dioxide can react with oxygen to form sulfur trioxide. Okay, please remember it can go one step further, and that step is an equilibrium process. Chlorine and argon does not react with oxygen. Okay. Now react with chlorine, same idea again. Sodium chloride, magnesium chloride, Al2Cl6, or you want to put here, or AlCl3, both also acceptable. Okay, now the one additional part you need to remember is this part. Unfortunately, SiCl4, but it's no longer solid, it is liquid. PCl5, liquid. Okay, and that's something that you have to know of lah. So SiCl4 and PCl5, liquid. Hold on. PCl5 liquid, right? Hold on. Yes, sorry. No, sorry. It is solid. This is from my old slides. I'm really sorry about this. This is from my old slides. Sorry about this. So it's not liquid. It is solid. So only SiCl4 will be liquid. Okay, SiCl4 will be liquid. The rest of them solid. Okay. Now, sulfur does react with chlorine to form SCl2, but there's no need to know the reaction. Chlorine and argon does not react with chlorine. Okay. So relatively straightforward. Now, for the reactions with water, you need to know two parts. One of them is sodium, the other is magnesium. The rest of the elements, no need to know. So for sodium, it will react with water to form sodium hydroxide and hydrogen gas. Now, as you can imagine, what happens on this is the sodium less dense than water. It will spark with a little bit of flame and float around in the water until the entire solid dissolves in there. Then the solution becomes alkaline. Because it is NaOH, the solution, the pH will be 14. I think relatively straightforward. So for sodium, it's okay. It is what you have learned in your previous studies. But the more complicated one now is magnesium. Magnesium got two parts. You must recognize when it reacts with cold water or it reacts with hot water, steam. Because it's two different things. If it's cold water, right, magnesium will react with water, so eventually will become magnesium hydroxide, okay, and form hydrogen gas. It's just that the reaction is very slow, and because magnesium hydroxide is not that soluble, right, so you'll see like a bit cloudy white like that one. Because of that, less alkaline, pH equals to 11. Same process like sodium. It is just that it is a lot slower. But magnesium will react with steam vigorously to form magnesium oxide, white solid, and hydrogen gas. This one is a very fast reaction. So please remember, cold water slow, hot water steam, very fast. Okay. Now we will talk about the oxides of period 3 elements. Let us look at all of them. Sodium oxide, magnesium oxide, aluminium oxide. Electrical conductivity in liquid form. Sorry, this is in liquid. Very good. Ionic bond, giant ionic structure, high melting point, because all these three are giant ionic structure, ionic compound. When silicon forms silicon dioxide, the melting point is very high because it is actually a giant covalent structure, but it cannot conduct electricity. P4O10 SO2 are simple molecular structure, low melting point, zero electrical conductivity. Inside there is covalent bond. Outside, the intermolecular forces are van der Waals forces. Hold on. P4O10 will be permanent dipole forces. SO2 also permanent dipole forces. Again, relatively weak compared to ionic bonding or covalent bonding throughout the entire structure. So therefore, low melting point, zero electrical conductivity. This one is gas, P4O10, solid, solid, all solids. Okay. So let me clarify right here. The only thing you need to remember is this one is gas. These two. The rest all here all solid. Yes, P4O10 is still low melting point compared to the rest, but when compared to SO2 and SO3, P4O10 is still relatively higher melting point. That's why it's still solid at room temperature. Okay. Now, we are going to look at the acid and basic nature of oxides. And what does it mean is that for all these oxide, right, what happens when it reacts with acid or base? If a substance can react with an acid, generally, if you look at this, because they all contain, actually more importantly, so not only react with acid or base, it's also important to recognize when you put them into water, what happens next. So if you realize we are basing this acid base based on Bronsted-Lowry acid theory of base. Okay, so for the first two, we call them basic. For the last three, we call them acidic oxides. And only in the middle, we call the middle one amphoteric. Okay, now to understand this deeper, let us look through at the reactions. Yeah, let us look at the basic one first. Sodium oxide and magnesium oxide is the easiest. Why? Now, for these two, right, add them into water, form sodium hydroxide, magnesium hydroxide, already basic solution. Because of that, can react with the acid themselves to form salt and water. So therefore, we can call sodium oxide, magnesium oxide, proton acceptor. The O accept the proton, forming water. So base. So these two are what we call basic oxides. Okay. Not only put into water, become alkaline solution, happily accept a proton from the acid to form water. So basic oxide. That's how we name them. Okay. Sodium oxide, magnesium oxide. We don't look at aluminum oxide first. We look at silicon oxide. Because later, I want you to contrast between basic acidic and then come back to amphoteric. Okay. Now, silicon dioxide, because it is giant covalent structure, does not, let me reiterate, does not dissolve in water. Okay, because it's like your silicon oxide, one of the main components of glass. Your glass doesn't dissolve in water. However, it's an acidic oxide because it reacts with the sodium hydroxide. Okay, and it forms this is, hold on, the actual name for this is sodium silicate. Sodium silicate. Okay, sodium silicate. So it forms sodium silicate and water. Now, you may ask why is that the case? Because I know it looks like silicon oxide doesn't donate any proton or anything, but in theory, it actually reacts with the base to form a salt and form water. Okay, so we call this an acidic oxide because it can react with a base. Okay. Okay, and actually there's one more thing. The idea this behind called an acid-base reaction is because Bronsted-Lowry theory got one more theory, which I'm not learning right now. So that's why this is called an acid-base reaction. But for now, accept that it's an acidic oxide because it reacts with sodium hydroxide. Okay. Phosphorus 5 oxide, okay, P4O10, is definitely an acidic oxide because the minute you add into water, form H3PO4. So you can imagine when you react with any sodium hydroxide or anything, first it reacts with the water to form phosphoric acid. Then the phosphoric acid will react with the sodium hydroxide to form sodium phosphate and water. So please do recognize that P4O10 reacts with water to give you phosphoric acid. pH 2. Okay. Sulfur dioxide happily reacts with water to give you sulfurous acid or sulfuric 4 acid and sulfuric acid if you use SO3, sulfur trioxide. Again, both of them strong acid, pH 1. Yeah. Okay. So as you can see, if you react this with sodium hydroxide, it's going to form sodium sulfide and sodium sulfate here. Yeah. So these two also can react with bases. These two also can react with bases, so we call them acidic oxides. So if anybody asks you a question like SO2 with N, let me give you an example. If people ask questions like SO2 reacts with NaOH, okay, what will the product be? First thing first, it's a two things product. Your SO2 will first react with H2O, forming H2SO3. Then only your H2SO3 reacts with NaOH, forming Na2SO3 and water. What am I showing you this is I want to illustrate. Should you face this type of question, divide into two parts first. First, react them to form what happens in water, then have it react with sodium hydroxide. Same thing with sulfur trioxide. Now we have an understanding. Metal oxides, basic. Non-metal oxides, acidic. What about the middle one? The middle one is what we call amphoteric. Again, aluminium oxide and silicon oxide, these two does not dissolve in water. But aluminium oxide is called amphoteric because right here, it reacts with both acids and bases. It reacts with both of them. When aluminium oxide reacts with sulfuric acid, you form salt, aluminium sulfate, and water. Basic nature. When aluminium oxide reacts with sodium hydroxide and 3H2O, you form, hold on, this is called sodium aluminate. Hold on, I cannot remember this at the top of my head. Yep, sodium aluminate. Okay, yeah, sodium aluminate. Okay, unfortunately, right, you realize, right, the rest is quite straightforward. As in, very easy to know how to get the product. Acid and base reacts to form salt and water. The salt, the cation comes from the metal, the anion comes from the acid. Very straightforward most of the time. But this particular equation did came up a couple of times. You have no choice. You have to memorize it. And yeah, you have to memorize it. Same thing goes for this part right here. This one have to memorize. The rest you can relatively figure it out by yourself, even if you forgot at the time. But these two equations that I mentioned, you have to memorize. It's a bit hard to figure it out one. So you have to memorize what type of product it forms. And the rest is a bit easier. Because you see, phosphorus 5 oxide, phosphoric acid. Sulfur dioxide, sulfurous acid. Sulfur trioxide, sulfuric acid. But silicon oxide, aluminum oxide, this one need to remember it a bit. Sodium and magnesium oxide easy. Form sodium hydroxide, magnesium hydroxide. So it is silicon oxide and aluminum oxide I would like you guys to pay attention to. Okay. Yeah. If you realize, unfortunately, pure memorization in all those categories. Okay. Now we are going to look at the chlorides of period 3 elements. Sodium chloride, magnesium chloride, aluminum chloride, silicon tetrachloride, phosphorus pentachloride, and SCl2. Actually, SCl2 can ignore, not really in the syllabus. But the idea for all of them is the same. Now, the only difference between the oxides and the chlorides lies in the middle right here. On the middle right here, very big difference. Why? Sodium chloride, magnesium chloride, just like sodium oxide, magnesium oxide, giant ionic structure, ionic bond, happily dissolve in water. I'm not going to say much about it, but this one I want you to take note of this 6.5. I'll explain that one later a bit, but you must remember, if magnesium chloride dissolve in water, you cannot put the answer for the pH to be 7 neutral. It has to be 6.5. Okay, these two dissolves in water. Silicon tetrachloride, phosphorus pentachloride, simple molecular structure with covalent bond, van der Waals forces among them. Actually, when you add them into water, it release HCl gas because it's so exothermic. And of course, the HCl dissolve into the solution. It will definitely become an acidic solution. Okay. So silicon tetrachloride and PCl5 will definitely react with water. Notice, reacts, not dissolve, reacts. Okay, because you're changing the chemical compound. Simple molecular structure, covalent bond inside them. Now, aluminium is a different ball game. Okay, aluminium is a different ball game. Aluminium oxide is indeed a giant ionic structure. Aluminium chloride is a simple molecular structure with covalent bond, and the intermolecular forces is van der Waals forces. It actually doesn't dissolve in water. It reacts with water to give you an acidic solution, pH around 3. These numbers here, please do not change them. These are the exact numbers you have to put into your whenever the Cambridge questions ask you about it. Okay. Why is this the case? Okay, so sodium chloride, magnesium chloride, I'm not going to mention much. It's going to dissolve a little bit. Dissolve. So this is the equation for it. Straightforward. No need for me to say much. Okay. Now for this, right, you have to remember this. Silicon tetrachloride reacts with water to form silicon oxide, solid, and HCl gas, which then dissolves inside the solution in order to give out resist HCl gas and will dissolve in water, and it will make the water, the solution inside there, acidic. Hold on, what I want to add? Oh, sorry, there's a slight typo mistake here. This isn't liquid, this is solid. Yeah, this is solid. So for PCl5 reacts with water to give you phosphoric acid and HCl, also making the solution acidic. You may say, sir, why the HCl gas one? Because these two reactions is so exothermic that it causes the byproduct HCl to become released as gas. Of course, some HCl will dissolve, but it is such an exothermic reaction. Actually, when you add these two, right, you see the reaction bubbling a bit one. It's because it is that exothermic of a reaction. SCl2 also have the relative thing, but no need to know because not part of your syllabus. Yeah. Okay. Now, aluminum chloride, let's come back to this. If you notice, aluminum oxide, aluminum chloride, they all got a bit special properties one. Pay attention. Aluminum chloride becomes acidic, right? Because it is a small ion. Your AlCl3 or Al2Cl6, right, really does dissolve first one. It does dissolve first. Initially, what it forms, right, it really forms Al3+. So what's wrong with it, sir? Al3+ dissolve neutral. Unfortunately, you're going to learn this in A2. It has such a high charge, right? And high dense, small, right? It has high charge density. It causes water molecules to surround it, right? And form what we call a complex ion, AlH2O6 3+. Okay, you're going to learn this in A2. So it actually forms this particular compound right here. Now, because it is so positive, so small, it causes water to donate its electrons to it, so forming what we call this complex ion. This complex ion then can dissociate to form AlH2O5OH2+ plus H+. It is this H+ that give your pH to be 3. Yeah, it is this H+ right there that give the pH to be 3. Yeah, that's why for aluminum chloride in water it reacts. It's because of this particular reaction. You're gonna learn more about it in A2. Okay. Oh, and we are done with the reactions of period 3 elements, period 3 oxides, period 3 chlorides. You may say, is this all you really have to know? Yes. Unfortunately, again, I have to emphasize to you, there are certain on highlight. You have to memorize, no choice. Like silicon tetrachloride reacting to form silicon dioxide, this one have to know. PCl5 to form H3PO4, this one must know also. Unfortunately. Yeah, so this is what I mean when now it's like a lot of memorization involved. Oh, sorry. Please remember, sorry, because it's my old slide, sorry. This is solid. Solid there. Please remember, this one cannot be liquid, it is solid. Okay. Okay. Now, the last part is something very factual. So this type of questions can come out in the paper as more like a either in multiple choice like a factual question or either in paper 2 like a factual question. So ceramics apply to any class of inorganic non-metallic objects subjected to high temperature. Can be giant covalent structure or giant ionic structure. What are the properties of ceramics? Highly resistant to heat, corrosion resistant, does not deform easily, wear resistance. Because of this, ceramics is usually the combination of two type of mixture of two types of substance with either have giant covalent structure or giant ionic structure. Because of that, so we usually use a mixture of oxides for this particular one. So for example, you want to use it for electrical insulator. Okay, so we often use aluminium oxide and magnesium oxide because in solid they cannot conduct electricity and you need to have a high melting point. for refractory materials for lining surfaces, okay, that means when you need to heat up high temperature, that time of molten metals, that sort of thing, we often use to create the furnace that to line it up, all that thing. We use a mixture of silica, aluminum oxide, magnesium oxide. Giant covalent structure, giant ionic structure, giant ionic structure. So magnesium oxide often used in furnace lining, high melting point, heating elements, good electrical insulator. Aluminum oxide, high temperature, high voltage, electrical insulator. Both of them are giant ionic structure. And of course, we have silicon dioxide, the giant covalent structure, to make as furnace for the production of glass, ceramic tiles, and things like that. So at the end of the day, if you want to think of ceramics, it's usually between these three. A mixture of silicon dioxide, magnesium oxide, and aluminum oxide. So this is what you need to know about ceramics. But actually this one is a bit too detailed on ceramics. If you notice your past year question, the way they ask for ceramic is generally quite straightforward. But if you want to remember one thing from this, please remember silicon dioxide, magnesium oxide, and aluminum oxide. Okay, but that's about it for ceramics. A minor point inside that. I would like you guys to remember that what is it? Yeah, the more important one is your chlorides of period 3 must remember all this. What's the pH, whether dissolve, whether react, what's the structure, what's the bonding, your acidic basic nature of oxides, the chemical reactions involved in it, and of course the reactions with water, chlorine, and oxygen, and even the color of the flame. Okay? And that's it for this chapter. We are done with chapter 10, periodicity. Thank you very much.